In this episode, I'm going to discuss two papers, and these are both related to things that I talked about in the main topic today. The first is a paper by Yan et al., and it's entitled Significant Sea Level Fluctuations in the Western Tropical Pacific During the Mid-Holocene. And this was published in the May 2024 issue of Paleoceanography and Paleoclimatology. So in this paper, they were investigating the past sea level changes in the South China Sea, specifically on Hainan Island. And they were interested in the Holocene sea level changes. So that includes a period that covers the past 7,000 years. And they used a proxy known as a microatoll. And first, I've mentioned microatolls before. And what is a microatoll? And what this is, it's a type of growth of a coral. So there's certain types of corals that grow in mounds, and one example is a species of corals known as Poroides. And what happens is Poroides will grow in a mound, and it will expand outwards and until it reaches the low tide level. So the corals cannot have to live underwater, so they cannot really survive a long time if they're exposed to the air. So if a coral grows up to the low tide level, basically it can no longer grow upwards. So these types of corals will only grow laterally after that, and you'll basically get a flat surface on top if sea level is constant. However, if sea level changes, then the corals will have to accommodate that sea level change. If sea level rises, you'll start to get a rim around the edge of the corals because the coral can then start to grow upwards again. And if sea level drops, then you get a sort of a staircase on the side of the coral. And as a result of this, microatolls are very precise way to measure past sea level because where the coral can grow is intimately related to the low tide level. So in the study by Yan et al., they sampled 9 microatolls, and these microatolls are currently exposed during low tide levels. So it's an indication that in the past, sea level was higher than present. And from these 9 corals, they all record at least a couple of different time periods of different sea level. So what they did is they sampled the corals and then did precise uranium-thorium dating. And that allowed them to figure out when these corals were growing. And because of the fact that they're microatolls, they can pinpoint what the past sea level position relative to present at a very high resolution. So these 9 microatolls that they measured grew between 4,000 and 6,500 years ago. And one thing that's noted is that the paleo sea level sort of, on the whole, shows a general lowering of relative sea level by about 80 centimeters during this period of time. And they didn't explicitly say this, but this is probably an effect of this ocean siphoning effect that I mentioned in episode 1. So, but on top of this, this general decline in sea level, there were fluctuations on the order of 50 centimeters of sea level changes detected in these microatoll records. And yeah, of course, they want to figure out why are these major fluctuations. And because these are microatolls, these are probably very robust records of short-term sea level changes on the order of centuries. And their hypothesis is that this is related to the so-called Walker circulation. So the Walker circulation is basically the air circulation pattern in the tropical Pacific region. And this comes about because of the difference in air pressure between the western and eastern sides of the Pacific. So it's driven by the fact that in the Indonesia region, there's generally a low pressure system, while in the Eastern Pacific, there's generally a high pressure system. And the difference in pressure is kind of maximized during La Nina events. And so during this period, the Walker circulation is quite strong. And because the wind along the surface of the ocean goes westward, that causes the ocean water to be pushed against Asia. And that can cause a sea level change on the order of tens of centimeters. And during an El Nino event, when the Eastern Pacific is much warmer, this high pressure system is not as strong. So basically, the water will go back towards the east, and it should cause a drop in sea level along the Asian coast. And what they presume is that when there were these excursions of relatively low sea level in this South China Sea record, that this was probably during a period when there was a dominant El Nino phase during the Holocene. So basically, like I said, like I said in the main topic, sea level changes can happen due to these sort of very short-term fluctuations in the climatic system. So one thing they noted is that some of the climate models have kind of predicted that the Walker circulation should weaken due to global warming, but thus far that hasn't been the case. So something that scientists are researching now. The second paper is by Svenevig et al., and it's entitled Rock Slide Generated Tsunami in a Greenland Fjord Rang Earth for 9 days. And this was published in the September 13th issue of Science. And what this was is that in September 2023, there was this unusual seismic signal that was recorded in seismometers all around the world. And it didn't look like an earthquake, but this persisted for several days, and in fact 9 days. And because we can say where the signal was, they quickly identified that this had to have happened in eastern Greenland. And they tracked it down to this place called Dixon Fjord. And if you don't know what a fjord is, it's basically a very narrow channel along the coastal regions of places that are kind of mountainous. And the fjord is dug out due to erosion from glaciers. So what caused this earthquake signal? It was from a rock slide, and what happened was that this chunk of the mountain adjacent to the fjord collapsed, and it caused a landslide. And it basically went through this valley that had a glacier in it, and it hit the glacier and it broke part of that off. And it may have also caused a bit of a submarine landslide as well. and all this material going in this narrow fjord basically caused this earthquake signal to start. And yeah, there was pictures from before and after this landslide, and you can see just how much material was taken away from the landslide. So all that material going into the fjord caused a tsunami because the water gets displaced. I mentioned in the previous segment about how Mount Unzen collapsed and caused this major tsunami in Kumamoto, but because this fjord is so narrow and so deep, the size of the tsunami was much bigger, and in places there's evidence that the tsunami wave was upwards of 200 meters high. So this was, very luckily nobody was there, but of course, if people were in this fjord, a 200-meter wave coming at you would probably not be survivable. And the fjord is quite restricted, but even in the adjacent fjords, in some places they said the tsunami was upwards of 6 meters, and there was research base where luckily nobody was there, but it's clear that tsunami wave went inland upwards of 80 meters and damaged the research base. So that's it was quite shocking, obviously. And this 9-day signal, what they think happened was because of the geometry of the fjord and the fact that the landslide went along the side of the fjord, it caused what is known as a seiche. So after the initial tsunami, basically, the wave would bounce off one side of the fjord and then bounce back, and then it keeps doing that. And basically it goes up and down and up and down. And this is what a seiche is. When I was a kid, we replicated the same kind of thing in our swimming pool, where everybody would have these little paddles that you could float on, and you'd go up and down and create waves, and basically over time the waves in the pool would start to cause the water to slosh out the sides of the pool. And the seiche, because the fjord is 500 meters deep and only a couple of kilometers wide, this sloshing, which happened every minute and a half or so, basically continued on for 9 days before it stopped being detectable in seismometers. And anyway, the main points they had is in the reason that this landslide happened is in part because the land is destabilizing because things are warming up due to global warming, and this kind of landslides that happens in a glaciated area, it's not unique. And, I published a paper on Greenland sea level change, and yeah, there was a few years ago there was a similar landslide generated tsunami that did affect a town in western Greenland. And they went back to the seismic records, and they found that in this Dixon Fjord there were 4 of these kind of landslides that happened before, obviously not as big. And in fact, another one happened in October 2023. And, in places like this, it's a big hazard, of course. And, the local government was kind of upset that the scientists that were conducting the study didn't notify the government that this had happened, and that they found out about it on the news. And yeah, it's something like this should really be communicated. And I don't blame anybody for that, of course. And scientists are going to be excited about this, and But there is a human dimension to our kind of research, and this is why I think it's important to do a podcast to sort of communicate why this happens. And, tsunami hazards due to glaciers collapsing in water is a big hazard in glaciated areas, and it happened in Alaska. There was a 500-meter high tsunami in a fjord in Alaska. I think it was in the 1960s, and that was the largest known tsunami in at least the past 100 years or so. And so one of the things that they talked about is how the tsunami probably wiped out all the archaeological records. And as a paleo sea level researcher, paleo or archaeological records often make up the best records of best proxies of past sea level in the past few thousand years. And it is kind of sad when these things are destroyed. But we do have to understand that in places like this, the geological record, especially things near the surface, are not necessarily permanent. So I do hope that things like this do spur more thorough research along the coast of Greenland, and that we can preserve and record the archaeological sites as well as the proxies for past sea level change. So that's it for episode 2 of the Raised Beaches podcast, and I hope you tune in next time. Thank you.